Hello, welcome to this chapter. In this chapter, we are going to learn the basic idea of what AI and machine learning is, as well as detailed introduction to how machine learning works, different types of machine learning, and some other information about machine learning. By opening the share folder on the Google Drive, we are starting our first step of learning. We should check the week 2 folder and download the whole folder and then unzip it and drag to our own Google Drive folder. And then we open the chapter 1 document with Google Colab. Google Colab is a free cloud service that allows you to write and execute Python code through your browser. It's especially useful for machine learning and data analysis. Colab notebooks are stored in Google Drive. It's built on top of Jupyter Notebook. Make it familiar and easy to use for those who are already using Jupyter Notebooks. Now, what is artificial intelligence and machine learning? Artificial intelligence, or AI, is a field of computer science that focuses on creating machines capable of intelligent behavior. Machine learning, a vital subset of AI, has evolved significantly since its conceptualization. Then we need to mount our Google Drive folder to the Google Colab. We can easily do it by using this code, and we can see our own Google Drive folder is here. These are 7 processes in the machine learning processing chain. Problem definition, identify the problem to be solved. Data collection, gather relevant data. Data preprocessing, clean and format the data for use. Feature selection and engineering, choose and engineer the most relevant features. Model selection and training, select an appropriate model and train with the processed data. Model evaluation, assess the model's performance using metrics like accuracy and precision. Model optimization, fine-tune the model to improve performance. These are 2 types of machine learning: supervised learning. The algorithm learns from a labeled dataset to map inputs to outputs, such as training an image recognition model to categorize new images using labeled examples. Below shows an example of supervised learning. It's simple linear regression. Unsupervised learning. The algorithm finds patterns or structures in unlabeled data, like grouping similar customers based on purchasing behaviors. Below shows an example of unsupervised learning. K-means clustering. Overfitting. This occurs when a model learns the training data too well, including the noise, making it perform poorly on new data as it fails to generalize. Underfitting. This happens when a model is too simple to capture the complexity of the data, leading to poor performance on both training and new data. Loss functions. These measure how far a model's predictions are from the actual values, helping to evaluate and improve model accuracy. Optimizers. These are methods that adjust model parameters to minimize the loss function, enhancing model learning and performance. Training and test sets. Data is split into these sets to train the model and then test its ability to generalize to new data, ensuring it hasn't just memorized the training data. Sea ice leads are significant linear breaks in sea ice caused by oceanic or atmospheric forces. They are vital for their roles in heat exchange, supporting marine life, aiding navigation, and participating in the carbon cycle, thus impacting global climate and ecosystems. These scripts are for how to create the dataset from iris. We need to mount first and then remember to change the bahas. We also need to adjust to the location. We take 100, 100, 300, and 400 as an example. Then we can run this and get to beautiful masks, and we can check if we find the region on the image is the one we care about. This script processes a dataset by extracting small patches around each pixel to create a richer set of data instances. Specifically, it avoids the edges to ensure each patch can fully surround the central pixels, generating a 3x3 patch for each using surrounding pixel data. This method enhances the dataset by incorporating spatial context, which is crucial for tasks like image processing and machine learning models that require a more comprehensive understanding of pixel relationships. The resulting array of patches is then used for further analysis or model training. This script processes a binary mask by trimming its boundary labels to ensuring consistency with previously extracted data patches. It excludes the outermost rows and columns of the mask and then flattens the trimmed mask to create an 1D array of labels. This is crucial for aligning labels with corresponding data instances, particularly when training machine learning models that require precise input label matching. This creates a balance between CIs and lead in our data. And we need to remember to save our data. Then to the next chapter, we need to load our data first. The same, we mount our Google Drive with Google Colab and we save this path. And then we import the data we have just saved. The next is CNN, which is a class of deep neural networks specially designed to process data with grid-like topology and originating from the visual cortex's biological processes. CNNs are revolutionizing the way we understand and interpret visual data. Below is a basic CNN structure implemented in TensorFlow. Random forest is a key machine learning method predominantly used for classification but also applicable to regression. It explores the use of decision trees as the foundational elements of random forest and explains the concepts of ensemble learning, decision trees, bootstrap aggregating, and feature randomness. These elements work together to improve model accuracy and robustness, enhancing generalization capabilities across various applications. Here is a code using function CLF, and we use it to define extreme reshapes. VIT is a modern approach in deep learning for image processing. VIT utilized the transformer architecture originally designed for natural language processing to handle image data by breaking images into fixed-sized patches, embedding these patches, and processing them through transformer models. Key elements discussed include tokenization of images, position embeddings to capture spatial relationships, the multi-layer transformer architecture, and a classification head that interprets the processed data to classify images. This methodology allows VIT to achieve strong performance in image classification tasks. This section discusses model selection and cross-validation in machine learning. It covers how cross-validation helps prevent overfitting and ensures models generalize well to new data. The text contrasts the use of cross-validation and validation sets in deep learning models like CNNs and VITs with traditional machine learning models, where techniques like k-fold cross-validation are more common. Also, there are different strategies for model selection, including hyperparameter tuning methods like grid search and random search, highlighting the balance between using validation during training and relying on cross-validation depending on the computational resources and project requirements. This is the code for k-fold cross-validation. This section explains the process of model selection using grid search, a common technique in machine learning for optimizing hyperparameters. Grid search involves specifying a set of possible values for each hyperparameter, training models on each combination of these values, evaluating them using cross-validation, and selecting the model with the best performance. Thank you very much for watching.